in Newtonian gravity that everybody learned about in high school physics, or maybe will be learning about in the future for some of the people here, this is sort of an instantaneous action at a distance where you have a force between any two objects that's proportional to their masses and inversely proportional to the square of the distance between them. And it's instantaneous, and it's just, that's what it is. You know, from that you can derive all the other laws of motion relating to gravity and orbits and things like that. But this really only works in the certain regime where you have small enough masses and slow enough velocities. And so in Einstein's relativity, which was introduced in 1915, we start describing gravitation not just as this sort of mysterious force that doesn't really explain like why or how, but now gravitation is described by the curvature of space-time. And space-time is really, it's this four-dimensional space that's the unification of the three-dimensional space that we live in and the fourth dimension, time. And it's really bringing all of them together to realize that they're not completely independent of one another. They do interact. And empty space, as you can see here, I've got a laser pointer. So empty space where there is no mass energy is flat. Straight lines are straight, everything's pretty vanilla there. Right? But when you start introducing mass, it distorts the space-time. And the more mass you have, the more distortion you get. And that distortion is really sort of like a compression, or you know, it brings it together there. So now straight lines are no longer really straight in the same way. And objects aren't going to travel in straight lines if they're passing through that region. So it's sort of like if you want to imagine on a trampoline. This is one analogy I kind of like to describe this distortion in space-time, is that an empty trampoline is a flat, empty space-time. But now if you were to take a bowling ball, put it at the center, it's going to pull it down. And now if you were to take, say, a little golf ball and roll it across the surface of the trampoline, where without the bowling ball there, it's going to roll straight across. But now with the bowling ball there, it's distorted the space-time, and its path will now be curved. And if it gets too close to the bowling ball, it's going to fall into it. And that's really how the space-time curvature is now what causes this gravitation, what we see as the gravitational force, right? Distorting these straight line paths and pulling things in. Okay? And Einstein's general relativity sort of brings together, you know, where the mass curves the space-time, and that curvature of space-time tells the mass how to move through space-time. Right? And Einstein's field equations is a horrible set of differential equations that if you want to actually find out an analytic solution for anything, you can solve that. It's very hard to do, except in some very simple cases. But there are numerical methods for solving that that are very useful in gravitational wave astrophysics. So gravitational waves were first introduced in 1916, again by Einstein, in a follow-up to his general relativity papers. And these are the propagating distortions away from, that really propagate out changes in the gravitational field. So how is something far away going to know about the gravitational field at your source point? Well, it's going to know it because of gravitational waves. And if it's a static thing, like the sun is for us here on Earth, then that's fine, it's a constant curvature. But if we were instead around binary stars, then that field would be changing over time. We wouldn't always feel the same gravitational pull depending on what relative position the two stars were in. So let's say we had a binary star system, they're orbiting around each other, you might see gravitational waves propagating out from that central orbit, kind of like this pattern. And sort of, now in our trampoline example, if we take two bowling balls and we get them moving around each other right at the middle, you're going to see ripples further out. And that's that propagation of the changing field. And these gravitational waves travel at the speed of light. It's sort of an intrinsic property in space-time we see, and relativity. Now it's important to note that at first Einstein thought these were really just a mathematical anomaly that, with the right coordinate transformation, they would go away. They weren't really there. And for a while, a lot of people did think this. But we are now quite certain that they are actually there, and we very much look forward to detecting them in the very near future. So what do gravitational waves do? Well, they stretch and compress space-time. So you can see the effect here on our little face, that as a gravitational wave passes through it, it's going to stretch it in the vertical direction and compress it in the horizontal, and then it goes back to normal, and then it stretches in the other way, and so on. And you see a little animation of that going on here to these concentric circles. As the gravitational wave passes through, they're going to stretch out, and then up, and out, and up, and back and forth like that. And it's also important to note that this stretching and compressing of the space-time, it's not actually moving the objects themselves, but what it does is it affects the measured distance between 2 points. So it's sort of an interesting concept where the things aren't moving, but the distance between them is changing, right? And that's just part of this non-linear, non-flat space-time here. And the analogy I like for this is if you have just a sheet of latex here, like the stretchy stuff they might use in tights or something. And if you were to put like a checkerboard pattern on there or some polka dots, let's say, as you stretch it, the dots themselves aren't moving on the fabric, but the distance between 2 dots changes. And so that's sort of the effect that the gravitational waves have, that they stretch and they compress. But this stretching and compressing is only really very small amounts, because gravity is a very weak force compared to the other fundamental forces. So the way it affects the space-time is what's called a strain, and it's a change in the length divided by the total length. So the further apart 2 things are, the more the space-time is stretched in between them, so the distance that you add on to the original is more. But we're measuring these relative changes in length to, you're expecting quantities of like 10 to the minus 22, and it's tiny. To give you an idea of how tiny this is that the distance from the Earth to the Sun, one astronomical unit, is about 150 million kilometers, so like 90-something million miles. Right? So a gravitational wave strain of 10 to the minus 22 over that kind of distance is a change in distance of less than the width of a hydrogen atom. It's less than an angstrom, less than a tenth of a nanometer. Now with electromagnetic waves, with light waves, you have vertical and horizontal polarizations, if you want to choose those coordinates. But gravitational waves, they're not dipoles, they're quadrupoles. So you don't have up, down, and left, right anymore. You have what we call plus and cross. And the polarizations for light are relative to like a 90-degree change in orientation. These are 45 degrees off. And you can see if you were to have like a ring of particles, the plus polarization is going to do like we saw on the faces on the previous slide. Or you can just rotate that by 45 degrees and you have the cross polarization. So I like to make an analogy that gravitational waves are like sound. Normally we're looking at the universe, so this is going to be a different way of observing the universe. So sound waves, as you might know, they compress and rarefy air. They're pressure waves in the air or whatever other medium they're traveling through. In that similar way, gravitational waves compress and rarefy the space-time that we're in. So while we see the universe with electromagnetic waves, light, we hear the universe with gravitational waves. The first efforts to measure gravitational waves were actually by Joe Weber at the University of Maryland, so right in this neighborhood. So back in the 1960s, Joe Weber at UM, he built these resonant bar detectors. So it's really 2 very large masses here. You have like the 2 halves you can kind of see. And they're connected in the middle with a little spring. So now you have this big resonator, sort of like a giant tuning fork, that's very sensitive at a very specific frequency. And the idea is that if a gravitational wave were passing through the Earth and through this detector at that frequency, that this bar would then resonate from that, and you'd be able to measure that. And you'd be able to isolate these bars from any other sources of potential disturbance at that frequency, that you'd be able to tell when a gravitational wave happened. So Joe Weber thought that he had a detection back in the late 60s. However, we now believe that it was not really a detection. There's really no way to confirm that he actually did have a detection. Kind of imagine if you have one ear, only one ear now, and you hear a ringing that then just goes away. And no one else heard it, and you don't hear it again. How do you really know what it was, or if it was even real, or not just some other noise? You know, was it gravitational waves? Was it something else? Chances are there was some noise source that Joe Weber hadn't really characterized or hadn't managed to isolate out of his detector, and that's what it was. And especially based on the kind of sensitivity of the detectors that he built, it's extremely unlikely that he actually detected a gravitational wave signal. Some detectors like these are still in use now, but they're not very sensitive compared to the methods I'll be talking about next, and they'll be taken out of use in the pretty near future. Following from the bar detectors in the 1970s, groups at MIT and Caltech developed this idea of using interferometric detector. And this is a standard Michelson interferometer. And the way it works is that you shoot a laser at an optical device called a beam splitter. And what this does is it sends it reflects half the light, and it allows the other half of the light to pass right through. So in this way, we're able to send light down these two perpendicular paths. And the fact that we have these perpendicular paths is very important because that's sort of the two directions of our gravitational wave influence. Okay, so the light travels down these two arms, and it will hit these mirrors and bounce back, going back to the beam splitter. Now, depending on how far the light has traveled along each of these arms going out and back, it's either going to come back to this beam splitter either in phase, where the peaks and the troughs line up, or out of phase. So now where the peaks from one direction line up with the troughs from the other. And that'll determine whether the light here interferes and comes back towards the laser, or comes towards this photodiode at this other port of the interferometer. And it's the relative length of these two arms that will determine which output the light goes to. So as a gravitational wave were to pass through this, what would happen is that the relative lengths of these two arms is going to change. So you'll start off with them being the same length. As the gravitational wave passes through, one gets longer, and the other one gets shorter, and the other thing happens. And this is going to create a pattern of increasing and decreasing brightness here at the photodiode that can be measured. And when you isolate out other noise sources and vibrations from this system, that oscillating signal here, that's your gravitational wave signal. And there's all other kinds of sensors and feedback channels on here that you can use to sort of eliminate other sources of noise from affecting this measurement. So, and this is able to measure very, very tiny distances, because what you're looking for is length changes that are relative to the wavelength of the light that you use, which is already going to be a very small number. And so if you can measure very small changes in the brightness there, then you're looking at very small changes in distance over the length of these two arms. And that's really how you're able to measure such tiny changes in distance over those arms. Now, and this basically is using the light of the laser as our ruler, probing the space-time between the different mirrors here. So LIGO is the Laser Interferometer Gravitational Wave Observatory, and that's the project that came out of these groups at MIT and Caltech in the 70s. They got funding from the NSF in, I believe, like 1992, the early 90s, to start construction of two sites. One is located in Washington State, the Hanford Nuclear Reservation, and the other one is in Livingston, Louisiana, kind of between New Orleans and Baton Rouge. And each of these has 4-kilometer-long arms. So imagine you've got that Michelson interferometer, but now this distance between the laser and the beam splitter and the photodiode, that's several meters. And then you go 4 kilometers all the way out to these mirrors at the other end. And it's important because you want those long distances, because the longer your distance you're measuring over, the larger the change in length will be, and that's your signal. So you need that, the longer the arms, the better. And about 4 kilometers is a pretty reasonable length for something that you're trying to build on Earth, where you have all kinds of other constraints. You need to be away from people and things like that. So we have these 2 sites that's 4 kilometers long down these arms. And Hanford, in the initial configuration, did actually house 2 different interferometer systems. One 4 kilometers long and the other one only 2 kilometers long. But with the upgrades to advanced LIGO, the shorter one has been eliminated. And these are placed far apart in order that we isolate potential noise sources between them. If you're listening to the universe, you don't want the noise from the ground to get in the way. And if you want to hear something with both ears, you can triangulate it better if your ears are further apart. It allows you to get a much more precise measurement on where your source is coming from. And we will know that the ground noise around them is completely different. So it'll be a signal that's the same in both detectors that will be a gravitational wave. And since gravitational waves are traveling at the speed of light, the 3,000 kilometer distance between them is about 10 milliseconds for light. So we'll expect a signal to happen in one and then the other, or possibly both at the same time, depending on where it is in the sky, with time delays of really at most 10 milliseconds. So if you have the same signal happening in both, but at delays of like a second, maybe that's an earthquake or something like that. And it allows you to really confirm your signal and eliminate potential noise sources. So now if we want some photos inside, this is your corner station of the interferometer. You'll have the beam splitter back here, and then there's some other optics in these chambers. And these are all big vacuum chambers housing these suspensions for the mirrors. And these suspensions serve to isolate the mirrors from ground vibrations and anything that could potentially interfere with the gravitational wave measurement. So you kind of get a sense of the scale of how big some of these are. And they're up on these seismic isolation pillars, and then you have these welded tubes that are evacuated. They're very close to perfect vacuums so that the air doesn't interfere with the laser signal that's traveling through there, and you can get the best signal possible, no extra interference. Here's a diagram slash photo of the optical table for the laser, because we get a very powerful, very stable laser that's specifically designed for this project, but we want to do even better than that. So there's additional optical systems in there that clean up the laser signal and help make it a very pure laser at an exact frequency, and help stabilize the power of the laser so that any variations we see in the interferometer output we know come from a gravitational wave signal and not from the laser fluctuating. These very large mirrors that we have are almost perfect. The laser operates at a wavelength of 1,064 nanometers. So this is just in the near infrared, just wavelengths just a little bit larger than what your eyes can see, so just past red. And although the mirror looks a bit clear here in optical wavelengths, which your eyes can see, to the laser light at 1064 nanometers, they are 99.999% reflective. So basically almost perfectly reflective. And there's nice coatings on the top of the mirror to help achieve that very high reflectivity. And they are very nearly flat. They are very perfect surfaces to have a radius of curvature of 4 kilometers. That way, as the light is traveling through these tubes, it continues to get refocused back down. Because normally laser light is going to disperse, and these mirrors help refocus that light back down so that you maintain the most power in the interferometer as possible. That helps give you the strongest signal when a gravitational wave passes through. So actually, there's special optical cavities in these arms. You might have heard of the Fabry-Perot cavity, and it helps stabilize the laser light, and you end up with actually kilowatts of laser power in these vacuum tubes. So if you were to look in, that would be the last thing you see. Yeah. So there was the initial LIGO configuration, and a few years, I guess several years ago now, in 2009, that finished science operations, and upgrades for advanced LIGO were begun. And advanced LIGO uses the same vacuum system as initial LIGO, but there's new optics, new laser, better suspension, a lot has been upgraded. And what this serves to do is just increase our sensitivity, and what we're expecting is an increase in sensitivity of a factor of 10. And because we measure gravitational waves by their amplitude, that means that this factor of 10 in sensitivity gives us a factor of 10 in sensitive distance, which means a factor of 1,000 in sensitive volume. So while initial LIGO was sensitive to this little bubble of local space out to about 20 megaparsecs, so like 60 million light years, a very local region of space, advanced LIGO, we hope to be sensitive out to 200 megaparsecs or further, so 600 plus million light years, a much larger region of our close space to include many local galaxies and clusters, and that means possibly 1,000 times as many sources to observe. So here we have the design, the estimated design sensitivity for initial LIGO, and that's in the dashed black line, and we got that pretty good. From our two detector sites, Hanford and Livingston, from the 6th science run back in 2008-2009, we have their sensitivity spectra. And so what we have here over frequency is the strain amplitude that they are sensitive to. So you want these curves to be lower. So the lower it is, that means you're sensitive to smaller strains, smaller gravitational wave signals. So the lower they are, the better. Any signal that pops over that sensitivity line, that's a possible detection. Right, so that's our sensitivity as of late 2009. And when the full design advanced LIGO is ready later this decade, that we hope to have a design sensitivity here, the solid black line, and that gives you at least a factor of 10 improvement on your sensitivity. So we get observe a lot more sources. And I kind of threw in here one example source. This is a neutron star binary, so a pair of neutron stars orbiting each other and merging at a distance of about 60 million light years. And you'll see that's kind of just beyond the sensitivity of initial LIGO. Maybe on a good day, you might be able to observe that if that were to happen. With advanced LIGO, that's going to be a very loud signal. So we're really looking forward to this. And actually later this year, probably by the end of the year, late September, October, advanced LIGO is going to start its first observing run, what we call O1. And that will run for about 3 months. And there we don't have the laser at its full power, and other things are still in progress as we do these. There will be, over the next few years, alternating runs of sort of time periods of commissioning, where we kind of work on the detector, improve it, advance it up, to get towards the full design sensitivity. And those will be interspersed with observing runs where we try and run the detector as much as possible and really learn about its operation when you're trying to keep it going 24/7. So this first one will be about just 3 months long, and already we're getting sensitive distances of, instead of about 20 megaparsecs, we are getting sensitive distances already of about 60 megaparsecs. So that's a factor of 3 improvement on sensitivity, a factor of 27 in the volume that we're sensitive to. And if we're really lucky, we might observe something. Because this 3-month run of advanced LIGO will be sensitive to the same amount of space-time volume, so sensitive volume times the time that you run it, as initial LIGO was in its full year. because its additional sensitivity makes up for the shorter amount of time that we're going to be running it. And by about 2019, 2020, we hope to be at that full design sensitivity and doing observing runs for like a year, 2 years, just as long as they'll give us funding for it. So some of these new features in advanced LIGO is we're going from a 20 watt to a 200 watt laser. This laser pointer is like 1 or 3 milliwatts, to give you a sort of a sense. So that's 100,000 times more powerful of a laser. And that increased laser power going through the detector is going to mean stronger signal. We also have these large 40 kilogram, up from 10 kilogram mirrors at the end. And the larger mass is going to mean a more stable system. And it also is going to help with the fact that this large laser power heats up the mirror. And that can deform the mirror and introduce thermal noise into the mirror. We have sophisticated seismic isolation systems. So initial LIGO used passive seismic isolation. That's going to be upgraded to active seismic isolation, which is going to really help down in this region. This is sort of where seismic noise matters the most. And is really the limiting factor. So that's how we go from this steep increase that sort of limits us to anything above 40 hertz to now going down to 10 hertz. And that means we can observe the same signals for a lot longer and potentially new signals at these lower frequencies that we wouldn't have been able to hear before. And also upgrading the mirror suspension to a 4-stage pendulum as opposed to just a 2-stage pendulum that also further isolates the interferometer and our detection from the surrounding environment and gives us better sensitivity. It's really, I think, like an engineering marvel that they're able to do this. But LIGO's not the only game out there. We have a global network of detectors in progress. Our main partner is Advanced Virgo, which is an upgrade that's currently ongoing from an initial Virgo. This is a French-Italian group that has constructed a 3-kilometer long interferometer in Cassina, Italy, right near Pisa, if you're ever in the area. And something else to see other than the Leaning Tower. This is an engineering marvel that works. And so upgrades are ongoing right now to bring this up to an advanced interferometer, kind of basically the same as advanced LIGO. And it's expected to be ready next year in 2016 to start doing joint observing runs with advanced LIGO. There's also the Geo 600 detector in Germany near Hanover. And this is a British-German collaboration, and it's only a 600-meter long detector, so it's not really sensitive enough to do astronomical observing, but it's an important test bed for new technologies that can be tested on what's really a full-scale operational interferometer. So it's a lot of new technology that's going to be put into advanced LIGO was first tested at GEO. The Japanese are currently building the Cabra detector in the Kamioka mine, which you might also know as being the home of the Kamiokande Neutrino Detector. And this is an underground detector, also 3-kilometer long arms. They have finished boring out the tunnels now and are starting to build the interferometer in there. And that'll be online later this decade. And it's also expected to be, to join the LIGO Virgo network as one of these very sensitive detectors. And not only are they underground, which helps in eliminating some seismic noise, but they're also going to be cryogenically cooling the mirrors. Because remember, these lasers heat up the mirrors, so they're going to try cryogenically cooling them as well, which I think is very cool. We're also hoping for the Indian government to provide funding for LIGO India. The second interferometer that would have been going in at Hanford is on hold to go to India. And we're hoping that they're currently scouting out potential sites for a detector and trying to get dedicated funding from the government for constructing a facility there. That's hoped to be another 3 or 4 kilometer long interferometer of the LIGO class, advanced LIGO class. And we're hoping that that will be ready in 2020 or 2022, something in that range so that it can observe along with LIGO and Virgo. And with this global network of detectors, that means that any gravitational wave that passes through the Earth, we can detect it at multiple sites, which gives us increased detection power because we'll be able to really combine all of the data together. We're all working together. This isn't really a competition. We're all helping each other out here because we need each other. And these are all basically adding additional ears. So not only more power, but you have better sensitivity to different parts of the sky. And with these ears, you can better identify where on the sky a source is. You know, with only 2 ears, you kind of get some directional information, but it's not perfect. Just pin it down to just one spot. With 3, 4, 5 detectors, we can pin down where these sources are much better, and that means that we can look for electromagnetic counterparts to these signals, which is very important in getting the most science out of them as possible. There's been work, actually the group at NASA Goddard is a group that's very important in this collaboration for the Laser Interferometer Space Antenna, the LISA project. And this was aimed to be a constellation of satellites flying in a triangular configuration here, each sending lasers back and forth from each other to create these interferometric arms here. Basically, these were your arms. And this constellation would orbit around the sun in Earth's orbit, just kind of trailing us, with 5 million kilometer long arms. So that means that it would be very sensitive, and would be sensitive at different frequencies that LIGO, which makes it a very good complementary project. However, after the recent decadal, in which LISA did get very good reviews, unfortunately funding isn't really there and NASA's backed out, so this is now mostly an ESA project, European Space Agency, and the ELISA project is hoping to get funding for a 2034 launch, so quite a ways off, but not dead yet. And it would be a bit less sensitive, but still very, very important. Still maintaining most of the science while reducing some of the cost. And it's really as efficient as you're going to get. Third way of detecting gravitational waves is something called pulsar timing. So now, instead of building our own arms out there in space, we're going to use clocks that are out in space naturally, even further away. So pulsars are rotating neutron stars that are sort of shooting these high, very energetic beams of radiation out from their axes. And if that axis is in line with the rotational axis, you kind of get this lighthouse effect. As it's swirling around, if you're in the way, you get a blip every time it passes by and shoots the signal towards the Earth. And some of these are rotating extremely fast, meaning that you get a blip on the order of milliseconds. And these are very stable systems, so they're very stable clocks. And with that, you can probe the space-time between the pulsars and the Earth by looking at how this timing signal changes. So if you know you have a very steady clock, and then all of a sudden those pulses come a bit further apart or a bit closer together, that's a signal of a gravitational wave passing through. And you can identify signals then and create the arms of your interferometers by correlating these signals between many different millisecond pulsars throughout the galaxy. Now, because these are so far apart, we're measuring very low frequencies, about 1 over a year, so nanohertz. So while LIGO was looking in the hertz range, ELISA is going to look in millihertz. This is down to nanohertz, very low frequencies. So these signals take years. So you need to observe these pulsars very precisely over many years. So this work is currently ongoing by a few different groups around the world. There's a European pulsar timing array, a North American pulsar timing array, and an Australian one, all working together with a little bit of competition, tracking different groups of pulsars and sharing that data with each other to get the signal out. The first kind of important sources that we're going to need sort of a background on are neutron stars and black holes. So these are the remnants of massive stars. So you build up your massive star, it goes through its main phase, and then it goes through the supergiant. And if it's large enough, at the end of its life, you'll get a supernova. And the result of that supernova can be a neutron star or a black hole. Now, if it's massive enough, no force is going to support that amount of mass and will collapse down to a single point, and that's your black hole. This point of space of infinite density, really, and there's that region around it where not even light can escape, hence the name black hole. And you know, a little picture there. And a neutron star is just a bit less massive, and these can be, it's a matter of about up to a couple times the mass of the sun, so like 1 to 2 times the mass of the sun, compressed down to a radius of only about 10 kilometers. So extremely dense matter. It's basically entirely nuclear material. And if you had some neutron star matter, about a grain of sand's worth, your fingers, that would weigh 10 tons. It's the densest object in the universe that isn't already collapsed down to a black hole. And these objects, they're compact enough, and they have strong enough gravitational fields that they can get orbiting velocities around each other and rotational velocities, things like that, that are near the speed of light and going fast enough that they'll generate measurable gravitational waves. So that's why we really need observations of these out there. And yeah, we're able to get measurable gravitational waves from things like neutron stars and black holes. But what kind of configurations? 4 main groups of sources that we're really expecting to observe with these different kinds of detectors. So the first one is stochastic gravitational waves from the Big Bang. These are sort of like a noise signal, you know, like the hiss you might hear on your radio if you're not tuned to any station, sort of a random background. So sort of like the cosmic microwave background pictured here, you'd have a similar gravitational wave background from the Big Bang, but while the cosmic microwave background is from about 400,000 years after the Big Bang, the gravitational wave background would be from the first instant after the Big Bang. So you're really looking at the immediate aftermath of the Big Bang and the inflationary period, if you're familiar with that. And there was news of potentially observing this last year with the BICEP 2 measurements. Unfortunately, it was found from other observations that this was really only galactic dust sort of mimicking the same signal. But we hope in the future to be able to observe this stochastic background. Similarly, in these supernovae, the end of a star's life, massive star's life, these bursts, if they're not symmetrical, which it's very likely that they're not, then these core collapse supernovae, the center of the star collapses in under its own weight, essentially. Those will also generate bursts of gravitational waves. So you'll get a broad spectrum of gravitational waves coming out in a burst form. On these spinning neutron stars, if you can imagine a little mountain forming on there, as that spins around very quickly, that will also produce a very constant source of gravitational waves. It'll emit energy at a very specific frequency related to the rotational frequency of the neutron star, and it'll be a very constant source as it emits this energy very slowly, since gravitational waves are very weak. And this will be like a constant ringing noise, sort of very specific tone that we might be able to detect in a gravitational wave detector. And lastly, the source that I spend most of my time investigating, and I think is really one of the most interesting ones, is chirping gravitational waves from merging black holes and also merging neutron stars. So this is where you have a pair of neutron stars or a pair of black holes merging together. And this chirping signal, sort of an increase in amplitude and an increase in frequency going together. It's sort of like a whoop sound. As it goes together, you get the increasing frequency and increasing amplitude. So this would be 2 neutron stars, and because they are smaller, they can get closer, and they can get going a lot faster than the 2 black holes would. So this will be going up to higher frequencies. These two, they're going to orbit around each other, and as these gravitational waves come out, that's energy leaving the system. So you've got these 2 objects rotating around each other, and there's a certain amount of gravitational energy bound up in this system, in this orbit. And gravitational waves, they take some of that energy out of the system. So when you lose that gravitational energy, it means they're going to fall in together. So now they're closer, and that means that they orbit faster and emit stronger gravitational waves, which means that they fall in faster to each other in a sort of a runaway process until they're spinning around each other very quickly. And then once they get close enough, they'll be able to merge together and form a single object. And in most cases, that will be a black hole. If you have two neutron stars merging, the total mass resulting at the end should be enough to make it collapse down to a black hole. And that final object should kind of ring down a bit as it comes down to this spherical black hole stable state. And that ringing is sort of like if you were to just hit a bell, you'll get some frequencies of vibration of that bell or this black hole sort of ringing out, damping down. And you can see these gravitational waves kind of coming out from there. And that's the kind of signal we would be looking to measure. And they're going to speed up, going faster and faster, and those signals getting stronger and stronger until they merge. And this would be the ringing down process at the end. So the two black holes are orbiting each other, and you can see the gravitational field lines changing as we're going to zoom out here and see things further out. You can see these field lines changing over time, and those are the waves propagating outward. And as they get closer, it's going to speed up, and then they merge. And because these are black holes, they're going to merge at a much lower frequency than a pair of neutron stars might. And then we have our final black hole at the end that's ringing down there. We haven't detected gravitational waves directly yet, but we do have some indirect evidence. And the best example of that is the Hulse-Taylor pulsar. So this was found in 1974, and the Hulse-Taylor won the Nobel Prize in 1993 for its discovery. And remember, as I said, as these two objects, as they emit these gravitational waves, they get in closer and the orbit becomes faster, which means that the orbital period decreases. And it's a cumulative process as for the orbital period decreasing. So this is a binary system of two neutron stars. One of these is a pulsar, which is what we're detecting, and that's allowing us to actually track the system and measure its orbital period. And that orbital period is about 7 hours and 45 minutes. And over the last few decades, that orbit has decreased in length by about 35 seconds. And that initial measurement back here in 1974 gave us our initial orbital period. Now from that initial orbital period and measurement of the masses, you can calculate how much energy is going to be emitted by gravitational waves. And that'll tell you how quickly the orbital period is going to decrease, and so on and so forth. And that prediction is this dark blue line. And that prediction is really just based off of this initial measurement. The subsequent observations over the decades are the red dots. And these red dots, they match up basically perfectly with the prediction back from 1974. And so that means we have a system here, a binary neutron star system, emitting gravitational waves, or losing energy at exactly the rate predicted by relativity in gravitational waves. So it's really good evidence that gravitational waves are being emitted by this system. Unfortunately, that 7 hours, 45 minutes period is too low of a frequency to be detected by Ligo. So this is not a potential Ligo source just yet. So this is what a typical binary black hole waveform might look like. Where you've got, this is really looking at the last 10 seconds of it. So you could keep extrapolating this further and further back in time before the merger, and it might have started millions of years before at much lower frequencies, but that's below our detection ability. And over time, the frequency increases, they get closer, and eventually, this is sort of our last 10 seconds of the life of these two black holes as separate entities. You can sort of see here the increasing frequency as these peaks get a bit closer and closer and closer. It's very easy to see the increasing amplitude here, getting right up to the very loud merger, where a lot of energy is released. And if we zoom in there, you can see that peak of the merger, and there's just here a little bit of very quick ringing down. Remember these two, this final black hole sort of rings down any non-spherical part of it out at a constant frequencies. And we want to measure that waveform because that waveform is going to tell us about the motion of the sources. It's going to tell us about the neutron stars or black holes that were originally in that source. So as they spin around, we can measure the shape of the waveform, and that's going to tell us about the masses of the two neutron stars or black holes, if they have any spin to them. And those spins can also cause the orbit to move around, and that'll introduce some modulation on the frequency and the amplitude of the signal, creating some really funkier looking signals in this very plain one here. The amplitude of the signal that we measure is going to tell us about the distance. So combining that with the triangulation from the different detectors, that'll tell us where in space this source occurred. And that means we can correlate it with other observations. So if we identify a gamma ray burst, a burst of very high energy photons, that could potentially be from supernova or merger of two neutron stars or something else. That means we can correlate with other observational information and learn a lot about the same source. We can also learn about the orientation that can tell us about how these systems form and a lot of stellar dynamics. So here's some examples of binaries, and each of these would produce a very measurably different signal. So we would easily be able to tell apart these three different signals in the Ligo detectors. So if we have a circular binary, where they're orbiting around in this sort of circular fashion with equal mass objects, or you could have a circular orbit with unequal masses. So now the heavier one is going to be closer to the center of mass, and this is going to produce a different signal to that, something that we can measure. And here's an eccentric equal mass binary, where they're kind of getting closer to each other and then coming out and closer and out. And that's going to produce a modulated frequency. So it's not going to be the same monotonic frequency change that you see in these examples. However, we don't really expect to see any elliptical sources, as ellipticity is something that would actually be radiated away very quickly by these sources. So by the time they're at frequencies that can be observed by LIGO, they should all be very circular. They tend to circularize themselves very quickly. We have the gravitational wave spectrum. And here we have the LIGO and advanced LIGO detectors, with also hopefully following that in the 2030s, the Einstein telescope, an even larger and more sensitive telescope to get another factor of 10, along with potential sources that LIGO would observe, these compact binary inspirals, supernovae, and pulsars. And in space, we have the initial LISA design, along with the new ELISA design that still maintains quite a lot of science, quite a lot of detections. A Japanese planned mission DeSaigo for further into the future, 2020s, 2030s. And here we have galactic white dwarf binaries. So a white dwarf is a remnant of a star about the size of our sun, and there are millions of binaries of these white dwarfs in the galaxy, and they're actually going to create a confusion noise background. There's just so many of them, you can't resolve them apart. But there could be potentially tens of thousands that we can resolve, and these will allow us to map out the distribution of these stars throughout the galaxy and can tell us about star formation history and where things are in the galaxy. It would be great science. There's also these massive binaries. So these are supermassive black holes with masses of millions times the mass of our sun, that you might find in the center of the galaxy, or the center of all galaxies. So when you have two galaxies merge, these two supermassive black holes will also eventually merge. And that's a signal that LISA would be able to detect. And we also have extreme mass ratio inspirals, where if you were to have a black hole about 10 times the size of the mass of our sun merging into one of these supermassive black holes, it's a wonderful probe of the space-time around the supermassive black hole, and a wonderful way to test general relativity, because you could get hundreds of orbits around there, potentially measurable by LISA before it finally falls in. And in the nanohertz range, we have our pulsar timing arrays. So we have our current international pulsar timing array, and once the square kilometer array radio telescope is operational around 2020. We'll be able to observe many more pulsars, and pulsars, we'll be able to measure them with higher, better timing accuracy, and that will improve our sensitivity there. And here we have this stochastic background, potentially from the Big Bang, or from populations of now supermassive binaries, where we have supermassive black holes of 1 billion times the mass of our sun merging. And this could be in the early universe or in very massive galaxy mergers. And we'd be able to measure these throughout the entire universe, essentially. So we're not just limited to our local neighborhood. And so now that we know what sources are out there, how many do we expect to detect? Well, with the initial Ligo and Virgo configurations, our expected event rates were actually really quite low. On the optimistic side, observing for just a year, you're only looking at maybe one, probably not. And so it was really very much a test of, can we do this? And now with the advanced Ligo and Virgo configurations, once they're in their full design sensitivity later this decade, now our sort of realistic numbers, because there is a very large uncertainty in these populations, since there's really no other way to observe these systems, is we could potentially observe tens or hundreds of events per year. And this is not just allowing us to do our initial detection, but also to start gravitational wave astronomy as a new science, where we now have hundreds of sources, and we're able to do population statistics and all kinds of great science with these. So we have binary neutron stars, neutron star black hole binaries, and binary black holes. All different kinds of sources that we might expect to see with LIGO out there. It can be very exciting. So what can we learn from gravitational waves? Well, quite a lot, because there are these populations of black holes and neutron stars out there that we really have no other way of observing. Especially the black holes, unless there's a star that it's accreting matter from, or a disk of matter that it's accreting from. There's really no way of observing these black holes out there. So we predict there's a huge population of black holes in our galaxy, in the universe, and we just aren't able to observe. No way to observe them with light. So with gravitational waves, though, we'll be able to see these all over, and we can start pinning down their populations and how many are out there. Be great science. We can connect these high-energy gamma-ray bursts with binary mergers or supernovae, and really learn about those systems. And once we start making enough detections, and detections at high enough power, then we can test if general relativity is even correct. Right now we believe it is, but it hasn't been tested in this regime yet. In this regime where you have relativistic speeds near the speed of light, and you also have extreme masses of black holes and neutron stars. And we'll also hope to learn about the properties of neutron stars and exactly what the matter in neutron stars is like, how it behaves. Thank you for having me here.